So thank you very much, Steve. And thank you, by the way, for putting on this conference for the last 3 or 4 years, and all of you for coming. This is the kind of effort we need to move this forward, as my good friend Dr. Esselstyn said this morning. Dr. Esselstyn also said, too, I remember, something to the effect that he's of an age now, like me, that we're really pretty passionate about this. I'm very passionate about it. I think this information is so extraordinarily valuable. I got into this business 62 years ago, a little while ago. I'm 116 years old. Now, more to the point, I'm 3 years younger than Dr. Esselstyn. I mean, 3 months younger, almost the same age. So we've been around the block a bit. But I want to talk to you about the subject, the science of nutrition. That's where I've been for all these many years. And it's been great fun working in this field. Also, it's rather controversial for a lot of folks. And we have a lot of family and friends and other citizens in our society who don't quite buy into it. So it's been really quite a challenge. But I do have to say, and I'll say it again, this is easily, in my view, the single most important and significant medical science of all. It's really quite tragic, as a matter of fact, and sad, that medical schools don't teach this subject. And so I've thought a lot about this. I spent about 20 years actually in national policy development, where the science meets up with the politicians, in a sense, and saw a lot about why it is that this kind of information is difficult to convey. So it's a big topic. It's a very big topic, and so as I think about this, and as I have become quite passionate about the idea we have something here that's really, really important. And I look, what's the best way to get this out there? Well, I'm maybe a little prejudiced, a little biased, but I think getting the science right is really important. We have a lot of people speaking to this issue, but unless we get the science right, then it may not have a sustainable power to go into the future. So I really want to talk about, in a sense, how I came to know this. I think some of you have heard parts of this story before, and apologize for that. But I'm trying to draw a big picture kind of thing to sort of convey the idea that it's important. As many of you know, this is me, as I say 116 years ago, whatever. I grew up on a dairy farm, milking cows, and then went away to school, to Cornell University eventually, graduate school, and did my doctoral dissertation, as a matter of fact, on trying to figure out, along with my professors, basically how could we produce more protein, especially animal-based protein, which we called high quality. That's where I came from. So my personal background, my original education, was all about promoting protein, and protein of that high quality kind, animal-based. Then I had an opportunity along the same track of going to the Philippines. In fact, I was a coordinator of a nationwide program of feeding malnourished children with my senior colleague at the time. And in an effort to try to address the question concerning malnourished children in poor countries, we were all about making sure they got enough protein. So as I look back, it was protein, protein, protein. And that's where we're going, and that's what, in fact, a lot of people thought. We really had to have more protein. But unfortunately, there was a question that I ran into on the golf course of all things one day. My colleague, who was a surgeon in the Philippines, was telling me about the fact that he and some of his colleagues were working on young children with primary liver cancer. And it turned out, because I was wearing another hat concerned with the area of nutrition, I got the impression that, and that's all it wasn't published, but I got the impression that the few children, or I should say the few families in the Philippines who were consuming the levels of protein like we do, their children were more likely to get liver cancer. And so that was enough to propelled me to come back home to Virginia Tech at the time and get an NIH grant to begin to question that issue. Because if we're going there to sell protein essentially, and then we see this kind of thing, we've got to resolve that question. Now so I'm going to share with you just a little bit of data here in the beginning on some of the original research that we did. But before doing so, I want to show this representation here and just give you some fixation on essentially what levels of protein mean what. It'll become apparent in a moment or two. But this is a sort of a range of protein intake, if you will, in the U.S. population. And we did our original studies on experimental rodents or rats, if you will, whose intake of protein or requirements for protein are essentially the same as about humans. In any case, let me kind of frame this level of protein. It'll mean something here in a moment. We require, as protein goes, we require about 5 to 6% of the total energy as protein. 5 to 6%. It's really quite low. It may surprise many of you. And then that was done way back in the 1940s and even earlier to establish that number, and it's been supported over the years. But that was done experimentally. The 5 to 6% or so was done experimentally. And so when it came time to tell this to the public for public information, they jacked it up by a couple of standard deviations, and they called it the Recommended Dietary Allowance, or RDA. So the RDA, many of you may have heard of that term, has been the guiding post in essentially about how much protein we need. Too often, people think that's the minimum amount. That's not. That's an ideal level. This has already been pushed up above what we really need. So the 9% dietary protein is fine. That's all we really need in theory. But our range of protein intake is somewhere between about 11 and 22, maybe even a bit higher. And our average protein intake is 17. 70% of which is coming from animal foods. So I just want to set that stage. So we in our society are consuming really excessive amounts of protein compared to what we really need. And the experimental levels that I'm going to briefly show you in a moment was comparing 5% with 20%. Okay, so 5% is down there, at the sort of minimum level. The 20% is up near the higher level. It's just above average. And so, as I said, experimental rats require about the same amount of protein as humans. So this is, I consider, relevant. After seeing or hearing about the information about children getting protein in the Philippines, this report came out from India. It was an experimental animal study. Again, they were interested in studying liver cancer like I was in the Philippines because it's a big problem in third world countries. And so they did a little study where they had two groups of animals, both groups of which had been exposed to a carcinogen that gives rise to liver cancer, and they decided to feed 20% and 5%. And their hypothesis was, and it would have been anybody's in those days, the higher levels of protein would have protected against the liver cancer. So that's what they were interested in doing. And so they did the study. It was the reverse. The animals that were fed the higher levels of protein, 100% got the cancer. The 5%, none did. So is increasing protein increasing cancer? That was the question. Really a kind of a tough proposition coming into the world, believing of the importance of protein. So now really quickly, I used that in our research early on to learn something about actually just the science, just fundamentally the science. What's going on here? So we were interested, for example, in learning what is the mechanism by which this really works. And so in addition, we wanted to see if we could replicate what had been done by the Indian researchers. This is a representation here, essentially, of the sort of time scale of cancer formation. Just for your information, cancer in theory, and reality actually, starts with a mutation. A normal cell is converted to a cancer cell by a so-called mutation. Chemical comes in, activates, binds to the gene, if you will, converts it, you get a new cancer cell. That's the first stage. The second stage is promotion. That's the time during which these cells start to divide. like infant cancer cells, and they start to divide over time. Takes quite a long time, maybe, in some cases. And the last is the progression. That's when somebody notices, oh, I got a problem here. They get diagnosed. And that's, of course, usually during the time of metastasis. And so it's pretty serious. So those in just a very arbitrary way, just kind of arbitrary. Initiation, promotion, progression. I want to just fall back on that a little bit. So here, I'm going to share with you some of the early studies we did that really got me to thinking about my own sort of background and my prejudice. Namely, if we study the question concerning the formation of cancer in these animals for the first 12 weeks, in this particular case, we were able to do that. This was done some years ago. It says 1992 there, but actually this was done in the late 70s and 80s prior to that. But in any case, we did this study. Let's see what happens here. Starting out with a genetic mutation, giving them 5%, like they did, no cancer. In spite of the fact that there had been a heavy exposure to the carcinogen or mutation agent, mutagen, if you will. 20%, look at that. So we're seeing here now, something was in agreement with what I just described what the Indian workers had done. So then we did something else, many different things, but I thought this really caught my attention. We said, what happens if we change the diet? Start out here, back and forth. And so we, for the first 3 weeks, 3% protein, 5%, 20%, 5%, and then 20% again, 5%. In other words, of all the things one of the major things I did during my career, actually, I think this year was one of the most significant, but still today, I'll come back at these, people don't want to hear this, that you can actually turn cancer on by higher protein intake and turn it off by pulling it down. That's a pretty extraordinary sort of demonstration, if you will. There's one more sort of wrinkle to this little story here. In this case here, we said, okay, what if all of them got the mutation? We just fed them 5% protein for a while, maybe 10 weeks or so. By this time, we assumed, okay, carcinogen is gone, no more problems. So we just came back later and gave them 20%. And these cancer seeds, still lying there, being dormant, got turned on. And that led to a very provocative idea. We all have, I'm jumping way ahead and I can't have the time to tell you all the other data, but basically we all have some cancer cells in our body, or would-be cancer cells, at least infant ones, and it's routine that they're there. Okay, and then at some point in time they start to grow, when later on we start fertilizing them with the wrong diet, essentially. So that was an exciting idea there too. So early genetic mutations don't disappear. They kind of hang around. All we need to do is kind of put some food on them, let them grow. So back to my little scheme here of talking about the way cancer forms and starts and grows and so forth and so on. Notice the second stage there, promotion. There was some evidence way back since the late 30s, and especially a little bit sort of imagining some interpretation involving lung cancer, smoking, that cancer could be reversible. People not know why, and it was an idea kind of hidden in the background, but nonetheless, promotion was generally accepted by those who were in the field as possibly being reversible. That certainly was supported by what I just showed you. We could turn cancer on and off. So then we came to another study, another question I should say, of knowing how does this work. By this time, I'm saying to myself, gosh, this can't quite be right. This is too striking. I felt like, in a sense, I was touching the third rail, because to challenge the value, the health value of animal-based protein was a pretty serious matter. So we wanted to get in and find out what is the mechanism, what's the biochemical mechanism by which this works. This is fundamental, I must tell you, to a great extent of the entire drug industry, because people like to find what is the mechanism, which enzyme, which this, which that might be causing the problem. Then you can find a chemical. I'll come back to this. You can find a chemical to block it. So we looked for, quote unquote, the mechanism. And I just listed a bunch here. In the beginning, the high protein diet, for example, did things like increase the rate of uptake of the carcinogen into the cell compared to the low protein. So, oh, maybe that's it. Just to eat more protein, more carcinogens getting in our cells and causing us problems. So we went on, and turned out, though, carcinogens, when they go into the cell, they get metabolized to produce products that are more active. So active, they bind to the DNA. Some pretty nasty stuff. That enzyme is in the liver. And so we wanted to see if the high-protein diet affected the enzyme activity. It did, 2 ways, within hours of consumption. The high-protein diet turned on the synthesis of that enzyme, so there's more enzyme. Now it can, form more stuff in a hurry. The second, it changed the characteristics of the enzyme, very complex molecule. It changed it in a way in which it also speeded up the rate of formation of these very reactive products. So we got 3 possibilities here. I'm saying, wait, which one counts? Which one are you going to deal with? And it increased the binding to the DNA, as I said. Then, in turn, it decreased our normal ability to repair that kind of damage that goes on all the time. This is a high-protein diet doing it. So then and I won't go into this kind of detail. The second phase, we kept on looking. There's a period of about 12 to 15 years. Very extensive research, and with a lot of graduate students and postdocs, and et cetera. And there are some things that are really exciting there. I could give a lecture on each one of those, or 2 or 3 hour lecture, but they're very exciting. And here's what came into view. I couldn't decide which one of those things is the key reaction. I mean, who knows? It's really difficult. But what that high-protein diet does with 10 of those reactions, there's 10 there, it turns on 8 of them. It increases their activity. That's interesting. Turns them all on. 2 there, it actually decreases. And it turns out those 2 that are decreased is DNA repair and so-called natural killer cell activity. We've got, it's more than one, but we've got 2 really important mechanisms in ourselves that will protect us as we go forward and we get exposed to carcinogens and so forth and so on. We got 2 mechanisms that kind of hold it. In other words, it repairs the DNA. When that happens, and it's a very efficient process, it probably repairs about 99.99% of those mutations that occur. So we're kind of in a safe territory. Nature's been pretty good to us about that. But high-protein diet does, not only does it speed up all the other stuff, it comes in and blocks the mechanism we have for our safety, our fail-safe system. And so it does also for the second one. The second one is the case where now the cell has it's become a mutation, it starts dividing. Now it's recognized as a cancer cell. The immune system steps in with this little thing called natural killer cell activity and kind of kills those cells. Really interesting. Now, when you stand back and look at this, you say, which one of those are important? And all of a sudden occurred to me, there is no such thing as one thing. Now, this is a really challenging notion for the drug industry. It's a challenging for the very concept of what drug development is really all about. That one nutrient coming in and doing this tsunami of mechanisms, and far more, by the way. This is just the ones we looked at in those days. And so this was an awareness, a consciousness, if you will, sort of saying to me, nutrients don't act, we don't consume a nutrient and it does this and then it causes that. That's what a lot of people assume. No. I'll come back to this. This is what I call a principle. It's a rather disturbing principle in many different ways. Okay? So what it says is nutrition, each nutrient is operating by multiple mechanisms. Exciting idea. Okay, that protein was casein. We were just using it because those of us in research, that's what was available. Casein is the main protein in cow's milk. So I'm thinking back, I was on a dairy farm milking cows and all that sort of stuff because milk has good protein in it. The protein that was turning on the cancer was casein, of all things. Incidentally, like other animal proteins, I won't get to defend that proposition at this point, but it turns out we sort of said, okay, what if we try some other proteins to see if they do the same thing? And we chose a couple of plant proteins, soy and wheat. And we fed them up to 20%. That's the higher levels you see. They didn't increase the cancer. So all of a sudden, wow, this animal protein is doing this. These plant proteins are not. It's, again, sort of an indication of we're onto something here. This is kind of exciting. It turns out animal proteins do tend to do things altogether like each other. They're a little bit different here and there. And plant proteins also do something different. So we have this dichotomy. These over here doing unfortunate things, and these over here little better things, okay? Incidentally, I've been in the cancer field all my life, and we do have, as a matter of course, a major program in the United States that's been going on for more than 50 years to check out the food, which chemicals in there that might cause cancer. Environmental chemicals and stuff like that we all worry about. There's a formal program to decide which ones are carcinogenic and which are not. I'm going to come back to that at the end. I'm just simply telling you about that. I've spoken several times to that particular group. It's a very official body, very official laboratory, and so forth, on the basis of the criteria that's used to determine which chemicals cause cancer, which ones can we call carcinogen, which ones don't. Casein is the most relevant carcinogen ever identified. And some of you may have heard me say that before. It's a very provocative idea. I was just discovering, as I was going through it, I was getting into more trouble all the time. See, something was happening. It wasn't in the textbooks. It wasn't in the scientific literature. And by the way, I was teaching for much of that time, either introductory biochemistry or a little bit later nutritional biochemistry, upper class nutritional biochemistry. So I'm in the territory teaching it like it should be, like we sort of assume it should be. I'm seeing this kind of stuff. It doesn't fit in these kind of ideas popped up from time to time, so I'm very conscious of the fact that it's a little bit disturbing. In this case here, I published a paper on this concept that carcinogens don't count like we think they do, and published that in 1980. Got a lot of attention for it at the time, but some thought, well, that's a bit of quackery, get out of here kind of thing. But it's still there. Now I'm going to show you one more dimension of this sort of walking through the science to get some ideas. So the question then becomes, does this apply to other diseases other than cancer? Maybe heart disease, maybe this, maybe that. And there's some data. You have to kind of get in there and look at the information on this particular point. But let me just tell you, just for a general proposition, that if we compare protein intake from 4% up to 20%, let's say, compare that against the risk of getting some disease, heart disease, cancer, diabetes, whatever. What we tend to see, and this is very traditional in nutrition, for a bit, we have a normal level of nutrient consumption that doesn't do anything. That's ideal. That's where our bodies are working well. So up to about 10%, as I said before, that's all the protein we need. Everything's fine. Only when it's in excess of 10%. I mean, protein is an essential nutrient. We all know that. We wouldn't be here if we didn't have adequate amounts of protein. So we only need up to 10%. But almost every one of us consume more than that. So we're asking for trouble by doing that.